Okay, so this is section 10.5 in our book, 9.5 in the older version of the book we use. And we're going to go back to the example we talked about in section 3. And we wrote out the series for natural log of 1 plus x. I told you it was a series that normally you would have memorized. And this is what we came up with. In section 4, you learned how to run the ratio test. So wherever I saw n, I put in n plus 1. And then I divided it by the original equation. I don't need this -1 to the n minus 1 because we're talking about absolute values. You could have it in there. It's just going to make your life more miserable if you have it in there. And don't forget the absolute values. Don't forget the limit. Make sure you tell me what your answer is. I know that when I clean this up, x to the n plus 1 divided by x, or x to the n is just x. And I know that that has to be less than 1, so x has to be between -1 and 1. But when we looked at the series that the book has, it says that the series converges from -1 to 1, and it's including the 1. And that's what this section is about. This section is all about testing those endpoints. Okay, so what we do once we get to this point is we plug in the endpoints for x. So here I plugged in -1. And here I plugged in 1. And we're going to come back to this. First, we're going to learn some of the tests. Okay. Remember that a series, I don't know what I wrote. With numbers represents just one single number. So if I have this series, this is just going to give me a single number, depending on what p is. So like if this was cubed, if p was 3, it'd be 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed plus 1 over 4 cubed. And a series with only numbers, this actually just adds up to one big number, right? Dot, dot, dot. Just one big number. To find the sum of this series, there's actually a test for this. P must be greater than 1. This is called the p-series test. If p is less than or equal to 1, you can never find the sum because the series adds up to this giant number. So looking at a couple of quick examples. The sum of 1 over n squared, that means that p is 2. The series converges because p is greater than 1. Here we have 1 over the square root of n. Well, then p is 1/2, right? The power of n is 1/2, so the series diverges because it's a p series with p less than 1. Now, 1 over n is a special p series. And in this case, p equals 1. So the series diverges because p is less than or equal to 1. But let's think about why this is true. The series 1 over n equals 1 plus 1/2 plus 1/3 plus 1/4, and it passes the nth term test. The nth term test says that it must go to 0, that the sequence of numbers must go to 0. But that just tells me that it might converge. If the series hadn't had terms approaching 0, we would have known that it diverged. But because the terms are approaching 0, we know that it might converge. So let's put it this way. I'm going to break apart the numbers. I have 1, and then I have 1/2, and then I have 1/3 plus 1/4. And the next 4 numbers are 1/5 plus 1/8. And then the next 8 numbers are 1/9 plus 1/16. And then we have the next 32 numbers, the next 64 numbers, the next 128. You get it. So I have 1, and this is 1/2. These two numbers added together give me a number greater than 1/2. The next 4 numbers added together give me a number greater than 1/2. The next 8 numbers give me a number greater than 1/2. The next 16 numbers added together give me a number greater than 1/2. So I'm basically adding 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2 forever, constantly. These terms are just not getting to 0 fast enough, so we cannot find the sum. Okay, so this is a special series, and this is called the harmonic series. So once you start talking about the harmonic series, we know that the harmonic series diverges. Okay, and I already know that this is going to be your favorite series, even though we haven't talked about it. The alternating series. The terms alternate. The terms are getting smaller and approaching zero. If all three of those things are true, then the series converges. It is that easy. Now this series looks a lot like the one we just did, but it's alternating, and it meets all of the requirements. The terms alternate. The terms are getting smaller, 1/5, 1/6, 1/7, those terms are getting smaller, and they're approaching zero. So this series converges. That's it. Done. Okay, so now I have -1 to the n times n. This series is -1 plus 2 minus 3 plus 4 minus 5. Now, a lot of times kids will say, well, it's alternating, it converges, but that's not true. Just because it's alternating doesn't mean that it converges. Those other two parts have to be true also. The terms have to be getting smaller, and they have to be approaching zero. And neither of those terms are true, so this series diverges. And I messed up here, but this is -1 to the n times n over n plus 1. That's -1/2 plus 2/3 minus 3/4 plus 4/5 minus 5/6. The terms are getting closer and closer to 1, right? When I take the limit as n goes to infinity, this series does not approach 0, it approaches 1, so this series diverges. And then also your favorite way to find error. You'll like this far more than the Lagrange error bound. If a series is alternating, the first term that you don't use when you're finding the sum is your error. So if I use the first 8 terms of a series, the 9th term is my maximum error. Easy, right? So here are the first 8 series, or 8 terms of the series. If I add this up, I'm using that to represent the sum of the series. And the first unused term is my error, so 1/10. But there's going to be another part of this question. The other part is going to say, is our estimate an over or an underestimate? Well, the next term is positive 1/10, which means our sum would be better if I added 1/10, which means that our series, this sum right here, is an underestimate, because it would be better if I added numbers. Okay, so there it is for those of you who are actually pausing and writing down notes. Okay, so again, it's a positive number, so that means our estimate was an underestimate. If we had used the first 7 terms, our error would have been the next term, which was 1/9 this time. And since that 1/9 is negative, our original answer would have been an overestimate. Now this is, you don't have to write this down. This is called the proof of God theorem. There's an error in it, which is what people fall for it. So I start with 0 equals 0. Well, 0 is the same thing as 0 plus 0 plus 0 plus 0 plus 0, and that goes on infinitely. And then I know that 0 is 1 minus 1, so I have 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. And I have a star here because that's where we make our error. And then I just rearrange things, so now I have 1 plus -1 plus 1 plus -1 plus 1. So this is 1 plus 0 plus 0 plus 0 plus 0, blah, blah, blah. So 0 equals 1. Oh my God, the world is collapsing. But right here is where we run into problems, because whoever came up with this idea forgot that if you're going to create a series, the terms have to be approaching 0 in order for us to use it to find sums. And these terms are not approaching 0. They're going back and forth between 2 numbers. Okay. This is the integral test. And I had you actually watch a video about this a couple of nights ago, so you may already know this. But all you're going to do is take the integral of an equation. If the integral exists, then the series, oh my gosh, I keep making dumb mistakes with my notes. The integral converges. Okay, so again, if the integral exists, then the series converges. I should redo this, but I'm not going to. Okay, so if I have the series 1 over n, I already know the series diverges, right? This is the harmonic series. Harmonic. But I'm going to run the integral test on it, which means I'm going to integrate from 1 to infinity. 1 over n dn. This is your improper integral, so you need to change that to a different letter. I'm going to call it b. So I have the integral from 1 to b of 1 over n dn. B is approaching infinity. I find the integral. I plug in my values. I get infinity. Since I get d and e, the series diverges. I already knew that, but that's what the integral test does. The direct comparison test, you should also like this one. Does the series converge or diverge? Well, I have 2 over n, and all I'm going to say is I know that 2 over n is 2 times bigger than 1 over n. 1 over n diverges, so 2 over n must also diverge. Here I have 1 over n plus 2. Right away I know it diverges. I'm going to compare it to 1 over n. It's basically the same series, so this must also diverge. Now we're going to go back to our example, the natural log of 1 plus x. And in this first part right here, I'm going to clean this up. And when I clean it up, I get negative 1 over n, because this 2n makes it positive all the time. And then when I subtract 1, that takes us back to negative. So this is approaching negative infinity. 1 over n approaches infinity. Negative 1 over n is approaching negative infinity. So we do not converge at negative 1. But at 1, when I plug 1 in, I get negative 1 to the n minus 1 over n, and that's the alternating series theorem. The terms are alternating, the terms are getting smaller, they're approaching 0. It's the alternating harmonic series. So I can put an equal sign here. Actually, right now I'm going to pause this, and then I will bring this back with more stuff from this section.